So problem 3-24, it says in problem number 1, we use a graph to solve an equation. In what other ways can a graph be a useful solution tool? Consider this equation, the square root of 2x plus 3 equals x by completing parts A through D. So go ahead and write that equation down on your paper for 3-24. That's what I'm doing now. And then I'll share that screen. Okay. So the square root of 2x plus 3 equals x. We want to solve this algebraically. So the first thing we're going to do is square both sides. The reason we square both sides is it gets rid of this square root on this left side. So we have 2x plus 3 equals x squared. Now we should recognize that we have a quadratic. Remember, a quadratic is when x squared is the highest power of x. So we need to get it equal to 0. So I'm going to subtract 2x and 3 to get 0 equals x squared minus 2x minus 3. You could have subtracted just x squared. I try to avoid that because I always like my a value to be positive. If we had subtracted x squared, we would have negative x squared plus 2x plus 3, which is fine. A is just -1, and it's a little bit trickier when you go to factor that. So we can factor this. We can do quadratic formula. You can complete the square, whatever works for you. Go ahead and try to solve that for x. So we get x equals 3 and x equals -1. All right. Part B says Miranda writes down the equations y equals the square root of 2x plus 3 and y equals x. So she went back to our original equation and she set the left side equal to y and the right side equal to y. And it says how many solutions does each equation have? So both equations here, separately, not together, both equations have infinitely many solutions. Again, that's individually. So if I look at this equation, y equals x, I know it's a line. Every point on that line is a solution. Y equals the square root of 2x plus 3. Take a second to think about it. You don't need to say it or type it, but do you remember what a square root graph looks like? That's what we did in chapter 2, one of those parent graphs. So that graph also has infinitely many solutions because every point on that graph is a solution. Remember, the square root looks like half of a sleeping parabola. So Miranda says she's going to graph them to check the solutions. How will graphing her help her check the solution? So by graphing these equations, she can find the solutions by looking at the x coordinates of the intersection points. So again, by graphing these equations, she can find the solutions by looking at the x coordinates of the intersection points. I'll write down here, ignore the y coordinate because y isn't part of the original equation. Which was the square root of 2x plus 3 equals x. Sorry, that says the square root of 2x plus 3. So again, if we graph these, and we're not doing it yet, that's just what they say to do, we would only look at the x coordinates, and we should get 3 and -1. So if I pull up Desmos or get out your graphing calculator, so I have the equations y equals x and y equals the square root of 2x plus 3. So let's go ahead and sketch this for part D. So the line y equals x, we know, has a slope of 1, so it goes through 1, 1, 2, 2, 3, 3. I highlighted those points so you can kind of see where they are to graph them. Okay, so this is our graph. And as we can see in our graph, we only have one intersection point. It's the point 3, 3. So from the graph, so only one intersection point. Which tells us there's only one solution. Even though back here, when we solved it, we got two solutions. So we got two solutions. When we graph it, we see there's only one solution, and that solution is just x equals 3. The other one we had was -1, but we see they don't intersect here when x was -1. The reason this happened, so we got two solutions here. When we graph it, we only get one solution. When we squared both sides of this, we ended up, and you don't need to draw this, this is just kind of explaining why it happens. This equation should really only have one solution. We got two because when we squared it, we created the other half of this parabola, this sleeping parabola. That's what we did, which would have given us that other intersection point there that doesn't really exist. I tried to cross it off after I circled it. Didn't really work. So that point doesn't exist because it's not part of our square root graph. So for problem 25, we're going to go back to part A and check our solutions. So again, going back to this equation here. So we have the square root of 2 times 3 plus 3. Does that equal 3? So 2 times 3 is 6 plus 3. So the square root of 9, does that equal 3? 3 equals 3. That works. But then when we check -1, we get 2 times -1 plus 3. Does that equal -1? So again, just plug in -1 to both sides of our equation, or both spots for x. So 2 times -1 is -2 plus 3 is 1. Does the square root of 1 equal -1? The square root of 1 is 1, which doesn't equal -1. So when we solved it, this is algebraically correct, but when we check it, it doesn't work. This is what we call an extraneous solution. So an extraneous solution, it doesn't mean you made a mistake. Usually when we check our answer and it doesn't work, it's because we made a mistake. This means you solved it correctly, but the algebra manipulated the equation. Here, we made the second half of the parabola to make it not true. So from this point forward, it's implied that you need to check all of your solutions. Because some of them will be extraneous. Problems that typically have extraneous solutions are often square root problems, sometimes absolute value problems. I know there's another one, I just can't think of it right now. But that's where you're going to see them most commonly. Okay. Do we have questions so far? Oh, so problem 26, I guess I kind of went ahead. Problem 26 is saying, why does this extraneous solution happen? Where would it appear on the graph? So it would appear right here. This is what I was saying. That extraneous solution would be right here. It would be the bottom half of the parabola. So I'm going to flip the page. So just to kind of put that in words and to answer the question, the extraneous solution of x equals -1 would be the bottom half of the sleeping parabola. That we created only by squaring the equation. It didn't exist originally. Does that wording make sense? I just kind of, so the extraneous solution would be the bottom half of the sleeping parabola that we created only by squaring the equation. It didn't exist originally because that square root graph we know is just half of that sleeping parabola. And then last one here, kind of going through the same process. After solving the equation, let me just get the book back open so you can see what I'm talking about. Oh, and let me answer that question to everyone in the chat to see if that makes sense. Okay, so problem 27, after solving the equation 2x squared plus 5x minus 3 equals x squared plus 4x plus 3, Gustav gets called to the office and leaves his team. When his teammates examine his graphing calculator to figure out how he found his solution, they only see the graph of y equals x squared plus x minus 6. Consider this situation as you solve these. So part A, you're going to solve that equation. Go ahead and write it down. So to solve this algebraically, you want to get it equal to 0 because it is a quadratic equation. So I'm going to just move everything to the right, or from the right side. So x squared plus x minus 6 equals 0. Same thing, factor, quadratic formula, complete the square. So your sides here would be 3x and negative 2x. x plus 3 times x minus 2 equals 0 when you factor it. And then remember the zero product property says if two things multiplied together give you 0, one of them is 0. So either x plus 3 is 0 or x minus 2 is 0. So we get x equals -3 and x equals 2. So again, we should check these. X equals -3. So we have 2 times -3 squared plus 5 times -3 minus 3. Does that equal -3 squared plus 4 times -3 plus 3? So again, I just took -3 and plugged it in for x and everywhere in this original equation. So remember your order of operations, you square this first. -3 squared is 9 times 2 is 18 minus 15 minus 3. Does that equal 9 minus 12 plus 3? 0 equals 0. So -3 works. And then we should also check x equals 2. So 2 times 2 squared plus 5 times 2 minus 3. Does that equal, you're checking it, 2 squared plus 4 times 2 plus 3? Two squared is 4 times 2 is 8 plus 10 minus 3. Does that equal 4 plus 8 plus 3? 18 minus 3 is 15 equals 12, 15. That also works. So both of these solutions work. Not everything is going to have an extraneous solution. So remember, actually, let me give you guys time to write that down. And if I'm going too fast, feel free to just type it in the chat or private message me even so everyone doesn't have to see it. Or if you want me to explain something again. So this was the original problem. And then I remember it says Gustav got called out of class to go to the office. And this is what his team sees in his graphing calculator. And it's asking, where does this equation come from? So this equation is what he got when he set it equal to 0. So this comes from let's say getting the original equation equal to 0. You can kind of see it right there. You don't have to draw the arrow unless it helps you. So he got that original equation equal to 0, and that's where it comes from. So this equation, y equals x squared plus x minus 6, has infinitely many solutions. Every point on the parabola is a solution. Let's put that in parentheses. So we know this is a parabola, just an x squared. Every point on this parabola is a solution to this equation. But again, Gustav was trying to solve this original equation. So the question in the book says, if I graph this, where do I find the solutions to this? So by graphing y equals x squared plus x minus 6, and I'm trying to be thorough here so that if you look back at this, it'll make sense. So by graphing that, I can find the solutions to 2x squared plus 5x minus 3 equals x squared plus 4x plus 3 by so again, we're going to graph this parabola and we want to know how to find these solutions. Remember, this equation came from when he got it equal to 0. And we know our solutions are -3 and 2. So if I look at the graph, we can see right here, these are the intercepts. Because those intercepts show us when y is equal to 0. That's that green line down there. So by looking, if you're finishing that sentence, by looking for the x-intercepts. Again, the original equation, we got it equal to 0, and that's what he graphed. So we wanted to know when the left side of the graph was equal to 0. The other option here for graphing, and you don't need to sketch this graph, I'll just show you again. We put this guy in our calculators, y equals this side and y equals this side, and found the x-intercepts. We could have also graphed y equals 2x squared plus 5x minus 3, and y equals x squared plus 4x plus 3. So let me type those in. 2x squared plus 5x minus 3, and y equals x squared plus 4x plus 3. So when I graph these two parabolas, I can see that the intersections are -3, 0, and 2, 15. So I wrote that on my paper. Those intersect at -3, 0, and 2, 15, which tells us that x equals -3 and x equals 2. Because again, you only look at the x coordinates. So you have the option on a problem like this where it's kind of a longer equation to graph the left side and the right side individually. You have these two parabolas, or you get it equal to 0 and graph one parabola and then just look for the x-intercepts. So both ways you get the x coordinates of -3 and 2, which is the last thing I wrote here. So they intersect at these points, which gives us these two X values, because again, we ignore Y. We only look right here and right here because Y wasn't in our original problem. That is all we have for today. If you need me to go back over something, if you have a homework question, if you need to talk to me about something else, we'll be here. Your homework tonight is 31 to 37. It should all be posted in Google Classroom under the announcements for the week, under classwork, and it's also posted in PowerSchool. But you are free to go. Otherwise,